Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 12th video lecture. We're talking about Riemann-Stieltjes disintegration, and today I want to get in 3 theorems about Riemann-Stieltjes disintegration, or preparatory background definitions that lead up to Riemann-Stieltjes disintegration. And the first one has 3 parts. And here it is. It says that the first part says, suppose that the upper Riemann-Stieltjes sum with a partition F and alpha minus the lower Riemann-Stieltjes sum is less than epsilon for some partition strip P of the closed interval from A to B and epsilon greater than 0, then the upper Riemann-Stieltjes integral sum with P star F alpha minus the lower Riemann-Stieltjes sum, is what I should say, with P star F alpha will be less than epsilon for any P star, which is a refinement of P. So that's the first statement. The second statement, part B, says suppose the upper Riemann-Stieltjes sum with a partition P minus the lower Riemann-Stieltjes sum with the same partition is less than epsilon, where we're going to give some notation for this partition, and that is we're going to denote the partition as x of 0 up to x of n, and epsilon is greater than 0. We're going to let S sub I and T sub I the arbitrary points in the intervals from x sub I minus 1 up to x sub I. Then the sum as I runs from 1 to n of the absolute value of f of s sub I minus f of t sub I times delta alpha sub I, that will be less than epsilon. And part C, if f is Riemann-Stieltjes integral with respect to alpha on A to B, and the upper Riemann sum minus the lower Riemann sum is less than epsilon, where P is a partition given by x of 0, x of 1, all the way up to x of n, and epsilon is greater than 0. And TIs are arbitrary points in the interval from x sub I minus 1 up to x sub I, then the absolute value of the sum as I runs from 1 to n of f of ti times delta alpha sub I minus the Riemann-Stieltjes integral, that will be less than epsilon. So we want to prove these three statements. Okay. These statements are easy to prove, and so here's the proof. We'll start off with part A. And what we'll do is we're going to suppose that the upper sum with this partition minus the lower sum with this partition is less than epsilon. And this is true for some partition of A to B with P. Where epsilon is greater than 0. What we want to do is we want to show we're going to let strip P star be a refinement of strip P. We want to show that the upper sum with this refinement of f and alpha minus the lower sum with this refinement of f and alpha is less than epsilon. Okay, this is very, very easy. Okay, so here's the first thing we know. By a previous theorem, we have that the lower sum with P, F, and alpha is less than or equal to the lower sum with the refinement F and alpha, and that's going to be less than or equal to the upper sum P with the refinement of F and alpha, which I'm running out of room, but I'm going to put it down here, is less than or equal to the upper sum with P, F, and alpha. And I used this argument in our last video lecture. If you take the distance, if you will, from this upper sum with P and the lower sum, since it's less than epsilon, it's going to force the distance between the upper sum with the refinement and the lower sum with the refinement to be less than epsilon. I'm going to do that here, but as we've used it before, but I'm going to put in the details in this proof. Namely, what we have is that the upper sum with the partition P, F and alpha, minus the upper sum with the refinement, alpha, well, that's going to be greater than or equal to 0. And similarly, the lower sum would be refinement minus the lower sum with just P is going to be greater than or equal to 0. So, if we add these two quantities together, so the upper sum with P minus the upper sum with refinement plus the lower sum with refinement minus the lower sum of the original partition, that's going to be greater than or equal to 0. So, the upper sum with P minus the lower sum with P, rewriting these terms, plus, or I'll say minus, the quantity, the upper sum with the refinement, and then minus the lower sum with the refinement, has to be greater than or equal to 0. And so that says that since this is greater than 0, this first part, since this subtraction is greater than or equal to 0, this first part, that's this expression, has to be greater than or equal to this expression. I'll write it this way. So I'll write down the smaller thing first. So the upper, which is part the refinement, minus the lower, the refinement, must be less than or equal to, yes, less than or equal to the upper without the refinement minus the lower without the refinement. And this was less than epsilon. So we've got the upper minus the lower of the refinements has to be less than epsilon. And that's what we want to show. So that is part A. Part B, we suppose that the upper sum minus the lower sum is less than epsilon, and we're going to say, this is for a partition here, and our partition we're going to note it as x of 0, x of 1, all the way up to x of n. And we have that epsilon is greater than 0. What we're going to do, so we're assuming that this is happening. What we're going to do is we're going to let Si and Ti, the arbitrary elements, so I'm just going to say the elements of x of I minus 1 up to x of I. And what we want to do is we must show that the sum, as I runs from 1 to n, of the absolute value of alpha of s sub I minus alpha of t sub I times delta alpha sub I is less than epsilon. So this is something we might be able to use later, kind of like a lemma. But the way we're going to prove this is we're going to concentrate on this part. And so we're going to note both f of s sub I and f of t sub I are in, or elements, of m sub I up to big M sub I. Remember, this was the minimum, if you will, the minimum output value on the subinterval from x sub I minus 1 up to x sub I, and this was the maximum. And so since these endpoints, input values are in the x sub I minus 1 up to x sub I, their output values have to be between the minimum output value over that interval and the maximum output value of that interval. So what the absolute value, the distance between f of s sub I minus f of t sub I, their distance from each other has to be less than or equal to the distance between big M sub I and little m sub I. Okay? It's a positive number, or non-negative number. Okay. Now let's look at this the subtraction between the upper sum and the lower sum. So the upper sum minus the lower sum. Okay. We know that that's less than epsilon, but what's it equal to? It's equal to the sum as I run from 1 to n of the maximum value minus the minimum value times alpha sub I. So the summation as I run from 1 to n of the f of sub I, or f sub s sub I, minus f of t sub I, this should be delta alpha sub I, times delta alpha sub I. This guy, well, these are all positive quantities, and so I'm going to replace in each one of the terms that we're adding something bigger. I'm going to get that it's less than or equal to this sum here, and that's equal to the upper sum minus the lower sum, which we know to be less than epsilon. So that proves what I wanted to for part B. Now for part C, we're going to let f be a Riemann-Stieltjes interval function with respect to alpha, and we have for a particular partition that the upper sum minus the lower sum is less than epsilon. And I'll say where P is denoted by x of 0, x of 1, all the way up to x of n, which of course is B. And epsilon is greater than 0. We're also going to let T sub I, those items, the T sub i's, are going to be arbitrary points in the subinterval created by the partition. So T sub I are arbitrary points in x sub I minus 1 up to x sub I. And what we want to do is we want to show, this was the statement, it was that the absolute value of the sum of the f of t sub I, so again, I runs from 1 to n, delta alpha sub I minus the interval maybe of f d alpha. That's going to be less than epsilon. That's what we want to show. So here's the way that we do this. The first thing we note is that the lower sum with this partition is going to be less than or equal to the sum of the f of t sub I times delta alpha sub I, as I runs from 1 to n. And so I hope this is clear. The reason that this is true is that this lower sum is a sum, from I run from 1 to n, of the little m sub i's. And the little m sub i's are the minimum values of f of x over the subintervals created by the partition. And this is just an arbitrary output value. So it's definitely going to be, this output value is definitely going to be greater than or equal to the minimum output value, which is m sub I, which is involved in this sum. But this is going to be less than or equal to the upper sum, because the upper sum involves the maximum output values, which are going to be greater than or equal to f of t sub I. And we have that the lower sum, f and alpha, has to be less than or equal to the Riemann-Stieltjes integral of f d alpha, which is going to be less than or equal to the upper sum. And so here, that means then so what I'll say is, without putting the details this time, that the absolute value, the distance, if you will, between this summation and this number, that's in the end, f of t sub I, delta alpha sub I, minus this interval, is going to be less than the distance between this sum and the lower sum, so the upper sum and the lower sum, but we know that to be less than epsilon. So that proves this fact. So what I'm doing is I'm saying, hey, look, we've got two numbers here who are in between these other two numbers. And so what I know is that the distance between the bigger, if you will, span, okay, the upper and lower sums, is going to be bigger than the distance between these two numbers in between the upper and lower sums. And that distance between these two numbers is their subtraction of inside absolute values. Okay, that ends this theorem that had 3 parts. And now we want to get to a theorem, 2 more theorems, have to do with Riemann-Stieltjes integrability. So we want 2 more theorems during this lecture. And both of these theorems are going to be, their proofs are going to be based on a previous theorem that said that a function was going to be Riemann-Stieltjes integrable if and only if, for each epsilon that you gave me, I could find a partition, if there can be found a partition, such that the upper sum with that partition minus the lower sum with that partition is less than epsilon. And so that's what we're going to use in these proofs of these 2 theorems. Here's the first theorem. It says if f is continuous. So the first theorem has to do with f, the integration of f, on a to b. Then f is Riemann-Stieltjes integrable with respect to alpha on a to b. And the before we do a proof, I would like to bring up some background information. So the proof is going to be based on some things about uniform continuity as well as that fact I mentioned just a few seconds ago. So let me back up and remember a few things. So recall, we had a definition that if we had a mapping F, so let F be a mapping from a metric space X into a metric space Y. We say that F is uniformly continuous on X if for every epsilon greater than 0, there exists a delta greater than 0, such that the distance in Y between, let's say, F of X and T, here I wrote down P, so F of P and F of Q, that's the way we get the definition, will be less than epsilon for all P and Q in X with the distance in X between P and Q being less than delta. That's a definition that we had in analysis 1. Another, recall, is that we have this theorem that said if we let F be a continuous mapping of a compact metric space, say X, into a metric space Y, then F is uniformly continuous on X. And a third thing I want to recall is that a closed interval from A to B is compact in X. All right, so uniform continuity is going to play a big role in the theorem that we want to prove, and so is that previous fact. And so here's some information about uniform continuity that we've had in the past. Okay, we're ready to get to the proof now of the theorem. What was the theorem? The theorem was that if F was continuous on A to B, then F was Riemann's still descendant. Okay, so here's where we're going to do it. we're going to let epsilon be greater than 0 be given. Our goal is going to make sure that we can find a partition such that the upper sum of this partition minus the lower sum of this partition is less than that epsilon. And that's going to make F be Riemann-Stieltjes integral by previous theorem. Okay, so here what we do, we choose an eta greater than 0 such that alpha of b minus alpha of a is times eta is going to be less than epsilon. Okay. The first thing I want to tell you is that, remember, alpha is involved, it's a function, it's involved in the Riemann-Stieltjes integral. And what we know about alpha is that it is monotonically increasing. Now that may mean that it's constant. If it's constant, then this part is 0. And so any, you can choose any eta greater than 0, this will be satisfied. If this is not a constant function, then this is positive. I'll divide epsilon by this positive number. And what we're looking for is an eta that's less than epsilon over this quantity. How can I know I can get that? It's because this number that I would have is not 0 then, and I can find something positive between it and 0. There you go. Find a rational number. Okay, so that's what we have. Now, since F is continuous, on A to B, okay, then F is uniformly continuous. On A to B, and that's because A to B is compact, and a compact a continuous functional compact set is uniformly continuous. That's one of the things we recall. Thus, there exists a delta greater than 0 such that f of x minus f of t inside absolute values will be less than epsilon, and that's true for all x and t element of A to B with x minus t inside absolute values being less than delta. So this is the metric in R, this is again the metric in A to B, which is in R. Okay. Now, if strip P is a partition of A to B such that the delta x sub i's, so that's the distance between consecutive partition values, is less than delta, I should say. And that's true for all I. Again, here we mean I running from 1, I think it's 0, up to n. Then, the output values, the maximum output value minus m sub I, okay, from these intervals, okay, will be less than A. Okay, that's good. So these maximum and minimum values are attained over this interval, and they're going to be less than eta because that distance is going to be less than A because of the uniform continuity. And therefore, the upper sum with this partition, any partition that satisfies this, minus the lower sum with this type of partition, that's going to be equal to this sum as I runs from 1 to n of m sub I minus little m sub I times delta alpha sub I. And that's going to be, it's going to be less than, here I'll replace this quantity with something bigger. It's the sum as I runs from 1 to n of eta times delta alpha sub I, which is equal to, I can pull out an eta every time, so sum as I runs from 1 to n of delta alpha sub I. And so here, the delta alpha sub i's, when you sum them up, we've seen this before, really in the last lecture. If I were to write all these out, most of the terms would cancel with each other, and we'd just be left with eta times, it would be alpha of x sub n minus alpha of x sub 0, which is equal to eta times alpha of b minus alpha of a. But we've chosen eta such that, if you remember, that that's less than epsilon. Okay? So we have created, and there's lots of such partitions, such that we've created such partitions such that if you look at the upper sum minus the lower sum of the partition, it's less than any particular given epsilon. And so that means, by a previous theorem, I'm going to write this out in a second, but it means by a previous theorem that F is Riemann still disintegrable. One of the questions that somebody might have is, how do we know when you get a partition that satisfies that the distance between any of these consecutive partition points is less than delta? And the way that you can do that, you start off with alpha, and you just move delta over 2 units forward every time. You just keep going until you get to B. Or get close enough to B such that the distance between the last one and the next to last partition value and B is less than delta. Okay, so to conclude this, so by a previous theorem, F is Riemann still disintegrable with respect to alpha. Okay, I'm going to look at one more theorem. It also has to do with F, but it also has to do with the alpha. Whoops. So it says if F is monotonic on A to B, and if alpha is continuous on A to B. So the only thing we had about alpha before was that it's increasing. And let me just say, then F is Riemann still just integral with respect to alpha. And that's the theorem. And again, one of the things that this proof is going to be hinging upon is that fact that if we give any epsilon greater than 0, if for every epsilon greater than 0, if for each epsilon greater than 0, there exists some partition such that the upper sum minus the lower sum is less than that epsilon, then F is going to be Riemann still disintegrable. That's the way we're going to get this fact to be true. So to prove, we're going to let epsilon be greater than 0 be given. Okay. Then here's what we're going to do. We're going to say for any positive integer n, what we're going to do is choose a partition such that the delta alpha sub i's will be equal to alpha sub b minus alpha sub a over n. Okay. So there's a question, how do we know we can choose such a partition for a particular natural number? Okay, and so let me explain why this can be done. Well, first of all, this can be done because, and then the first thing I want to say is, if alpha is a constant, then any partition works. Because you'll always get 0 for the delta alpha sub i's. 2, we use if alpha is not a constant, we use the following process. Okay, so I'm kind of thinking for any n, okay, you have fixed n. We note that alpha of A, remember this is going to be increasing, okay, is less than alpha of A plus alpha of B minus alpha of A over n. Okay. So this is the breaking up the distance between alpha of B and alpha of A into n parts, and I'm just going to add one of those distances, or 1/n of the distance between alpha of B and alpha of A to alpha of A. And that's going to be less than alpha of B. We didn't make it to it, okay? And so this is some number in between these two output values. And so since alpha is continuous, we're thinking about, since alpha is continuous, we're thinking about the intermediate value here. So what that says is there exists an x sub 1, where's it going to be? It's going to be in between A and B, this x sub 1, element of A to B, such that alpha of x sub 1 is equal to alpha of A minus, plus alpha of A, alpha of B, I should say, minus alpha of A, all over n. That's what I have. And this is by the intermediate value. note, and continue this kind of line of thinking, that alpha x of 1 is going to be less than alpha of A plus 2 times the quantity of alpha of B minus alpha of A all over n, which still is going to be less than alpha of B. So here you went 1 over n distance of the distance between alpha of B and alpha of A, and you added that to alpha of A. Here we're going to add 2 times that, okay, that distance. So we got a little bigger. We still may not be up here. We're going to work. We're assuming here maybe n is bigger than 2, if you will. And so since alpha is continuous, okay, there exists an x of 2. It's an element of x of 1 up to b, such that alpha of x of 2 will be equal to this quantity, the alpha of A plus 2 times alpha of B minus alpha of A all over n. Okay, we continue this process until we have until we have alpha x of n minus 2 is less than alpha of A plus n minus 1 times alpha of B minus alpha of A all over n less than alpha of B. And again, since alpha is continuous, there exists an x of n minus 1 element of the x of n minus 2 up to b with alpha of x of n minus 1 is equal to this quantity. Then our partition is defined by, in this case, it's alpha, it's A, okay, that's x of 0, it's x1, x2, all the way up to x of n minus 1, and then b. That's our partition. Okay. Now, here's a case. So that argument was why we can form the partition that we claimed, okay? And that there was a partition such that the change in the outputs of i's was going to be equal to alpha of b minus alpha of a all over n for any fixed n. So case 1, if f is monotonically increasing, so remember we're having that f is a monotone function, then what we'll have is big M sub I, the maximum value over some subinterval, will be equal to f of, so we're increasing, so the f of x sub I, and the minimum, little m sub I, will be equal to f evaluated at x sub I minus 1 for any subinterval. then what we have is the upper sum minus the lower sum will be, this partition we formed, will be equal to, well, it will be the sum as I run from 1 to n of m sub I, big M sub I, minus little m sub I, times delta alpha sub I. But we have an answer for this. This is equal to the sum as I run from 1 to n of big M sub I minus little m sub I. Okay? And this delta alpha sub I, remember that's alpha sub b minus alpha sub a. For any fixed integer that I want, I can do this. So I haven't really declared what this n is, but I can write it in this form. And so that can be taken out. So it's alpha b minus alpha a all over n times this sum as I run from 1 to n of big M sub I minus little m sub I. Okay. But remember, we've already said what big M sub I and little m sub I is. It's alpha b minus alpha of a n. And here's the sum. Gosh, running out of room. Let me put it down here. And here, this is the sum as I runs from 1 to n of f of, this will be x sub I minus f of x sub I minus 1. And then a lot of this will cancel out, and we're left with alpha sub b minus alpha sub a all over n, so no matter what n we pick. And then this will be times f of b minus f of a. What we do is that we choose n. This will be true for no matter what n we pick, okay? So choose n. N such that epsilon over alpha sub b minus alpha sub a times f of b minus f of a is less than n. So we choose n since that happens. I didn't write that correctly. We choose n is bigger than, if you will, it's supposed to be alpha sub b, oh, I made a mistake, minus alpha of a, all over, epsilon times f of b minus f of a. So I made a mistake, I should have solved for it. I want that quantity over here. I want this quantity way over here to be less than epsilon. So I'm going to solve, I want this to be less than epsilon right here. So I'm going to solve for n, and I would multiply everything by n and divide by epsilon. And so I get this result. And this is what I want. And so we can choose an n that allows that to happen because the set of natural numbers are not down below. And thus, F is going to be Riemann interval. Riemann still just interval. And then case 2 is based on F is monotonically decreasing. then f of f, then m, little m sub I is equal to f of x sub I, and big M sub I is equal to f of x sub I minus 1 in that case. So the upper sum minus the lower sum will be equal to the sum as I run from 1 to n of the bigger value on the subintervals minus the smaller values on the subinterval delta alpha sub I, which would be equal to, if I skip a few steps, we know the delta alpha sub I is because of the way the partition is chosen, alpha b minus alpha of a over whatever n we've chosen. And here, this is going to be sum as I runs from 1 to n. Here, this is going to be f of, the bigger value is f of x sub I minus 1 minus f of x sub I. And those will cancel out, and we're going to be left with alpha sub b minus alpha sub a all over n. And this is just going to be f of a minus f of b. And so lastly, we want that last thing that I've written to be less than epsilon. So what we do is we choose n. What we do is we choose n such that we have alpha sub b minus alpha sub a all over epsilon times alpha sub a minus, f of a minus f of b. That quantity is less than n. Thus, we would have that f is known as Riemann interval, Riemann-Stieltjes interval functions with respect to alpha. And that proves this one. Ladies and gentlemen, that's enough for this lecture. Thank you for your time and patience.